Hello everybody, my name is Adel Najaran2C and today I'm going to talk about innovation and trends in cloud computing. Thank you for attending this keynote talk. Uh, Before going to the topic, I want to give you a brief introduction about myself. I am a postdoctoral research fellow at the University of Melbourne. I've got my PhD in 2015 from the same university, and my thesis was on inspired resource management and pricing techniques for cloud providers. And my research interest includes cloud computing, software-defined networking, energy efficiency, and green computing, soft computing, and machine learning. I have over 24 publications in high-rank venues, including 14 journal papers and 10 conference papers. My current H-index is 15, and my publication received 1,000 plus citation based on Google Scholar. Currently, I am working on traffic engineering for energy efficient consolidation of VMs in software-defined clouds, cloud data centers that they have software-defined networking as a network manager. The outline of this talk is as follows. We are going to talk about cloud computing, what is cloud computing, and why cloud computing has revolutionized the IT industry. And then we are going to talk about Gartner hype cycle for cloud computing. Gartner gives us a broad view about what are the trends and what are the emerging paradigms in cloud computing. Then I'm going to talk about cloud computing challenges, and as part of this we are going to talk about three recent studies that we did to address some of these challenges in cloud. The first study is an auction mechanism for cloud resource pricing, and then I'm going to present a framework for geographical load balancing to better utilize renewable energy, and our low-cost testbed for software-defined networking research that we built in our lab is the third study that I'm going to talk about. Finally, I conclude this talk with summary and conclusions. As you might be familiar or in traditional computing, if you are the owner, if you have been the owner of a IT company, or you wanted to provide some services to the community, first thing you need is to build your own infrastructure. So you have to buy and own your infrastructure for that service. So you need to buy hardware, system software, applications, and everything you want to build that infrastructure. And often that infrastructure should be big enough to handle the peak load. In case, for example, you have a web application, you need enough servers to handle the peak load in case that you have lots of users using your website. But most of the time your infrastructure is not fully utilized, and this is another issue of that traditional computing paradigm we know. This includes installation, configuration, test, and verification, and lots of management, and requires high capital investment. And based on common practice, every 18 months you have to update your softwares, your hardware, and everything. But what cloud computing provides is that you can subscribe for some sort of services, and then you can use that service and you pay as much as you want. And this is the benefit of clouds. You have the scalability and elasticity feature. If you need more resources, you can buy more, and if you don't need resources, you can release them. So overall, cloud computing allows businesses to outsource their IT facilities to cloud providers, and this avoids expensive upfront investment for establishing your own infrastructure. Cloud computing, in fact, is a long-held dream of computing as a utility. So we can say cloud computing is the fifth utility, like telephony, or water, gas, and other utility. And the good feature of cloud computing is that you can pay whatever based on for whatever you are using, and everything in cloud environment is virtualized, and you are getting virtualized software and hardware in form of a service. Uh, as you might be familiar, cloud services are offered in different layers of cloud services stack. For example, we have at the bottom layer we have IS cloud providers, or infrastructure as a service provider. These sort of providers, they offer you hardware or infrastructure as a service. You are getting, for example, virtual machines, networking, storage, and everything in form of service. On the top of IS cloud, we have platform as a service. These kinds of cloud providers gives you a platform or programming tools or components that you can own. You can build your own cloud application based on this framework that they give you. And on the top of the stack, we have software as a service. Software as a service is like a service that you are getting the direct access to a specific application. For example, something like online Excel that you can use, and you can pay based on whatever you are using. The scalability part and failure handling and everything is supported by cloud provider. Uh, in this slide, I want to talk about Gartner Hype Cycle. Gartner is an American research and advisory firm providing information technology related insight for IT and other businesses around the world. And the Hype Cycle is a graphical representation developed for representing maturity or adoption and social application of a specific technology. You can see some technologies are emerging and they are going to the peak, and then after a while they are going to the slope, and finally they become available for public usage and become established, and it can be used by public for their purposes. So here I have the Gartner Hype Cycle for emerging technologies in 2017. For example, here you can see some of the new technologies that are coming to the picture. For example, something like 4D printing or smart dust, and some of the technologies that they are already on the peak. For example, deep learning or machine learning or IoT platforms you can see here on the peak. So these days you're hearing lots of things about IoT platforms and deep learning techniques. And some of the technologies now they are in the deep. For example, augmented reality or software-defined security are in the deep, and after a while they become established and they can be used by public. For example, virtual reality is something that these days is happening in reality, and you can see that softwares and technology built based on this IT paradigm. In terms of cloud computing, we are seeing some emerging topics like blockchain PaaS or multi-cloud or serverless PaaS, and at the peak we can see edge computing these days, or IoT platforms, container management, or cloud marketplaces. At the Some of the technologies or paradigms are in the deep, like software-defined network, software-defined anything, hybrid cloud computing, private clouds that they are already investigated, and they are going to be a public technology. Some of the climbing up. Some of the technologies that are climbing the slope is, for example, something like a platform as a service, public cloud, and infrastructure as a service, and something which is already very established is a database platform as a service. So these days we are living in a digital transformation world. So lots of new technologies and new applications are appearing, and you can see, for example, things like smart cities or lots of smartphones and 5G or Internet of Things. For example, Ericsson predicts that in 2020 we are going to have more than 6 billion mobile devices, and number of IoT devices in 2017 exceeded the population of the world, and by 2020 we are going to have about 25 billion Internet of Things or IoT devices. As Cisco predicts, a city of 1 million will generate around 200 million gigabytes of data per day by 2020. All this shows that lots of applications and lots of more services are required to handle all these technologies, and we need more clouds and more apps based on what we are seeing these days. So if I want to give you a very brief introduction or about what are the online activities every second happening in our world, in a data-driven world that we are living, you can see some of these examples. For example, 3.4 million emails are exchanged every second. It's just a second like this, and 3.4 millions are already exchanged. So 6,000 tweets, 100,000 searches happening in Google every second, and you can see other stats here in this slide. So all these activities should be handled by some sort of application residing in data centers or cloud provider services should be handling these services. These online activities. So cloud computing at the first place had so many issues and lots of challenges that should be solved by researchers and other practitioners. Some of them are already solved, and some of them are still open, and people are doing research. In this talk, I'm going to talk about some of these challenges and our studies for addressing these challenges. For example, pricing and energy efficiency, virtualization, and consolidation of VMs. So the first study I want to talk is an auction mechanism we developed for pricing spare capacity of a data center. For example, we have a cloud provider, and this cloud provider has some spare capacity that cannot be sold on normal markets like on-demand and reserved market, and they want to sell this spare capacity. So we are going to present our method for pricing that spare capacity, an auction mechanism that we designed. So computational resources in cloud data centers are non-storable or perishable commodity. By this I mean, for example, if you have a server and you are not selling resources on that server for example, for 5 minutes, so you are wasted your capacity for making money out of that server or resource. So, and you cannot store this capacity. So the other thing that I want to talk here is that demand for these computational resources are not uniform over time, and we have more requests in some period of time, and then sometimes we don't have requests. So dynamic form of pricing is a good good example of a way that we can apply for handling these situations in clouds. So motivated by dynamic cloud pricing, we designed an auction mechanism to price resources in clouds, especially in infrastructure as a service cloud provider. And auctions can have different types of goals. For example, an auction can be truthful, or an auction can try to maximize revenue, or can be fair. For example, truthfulness means means that if a user or a client of a cloud submits a bid for using a specific type of resource or service, that bid, that user cannot make any, for example, that user cannot play with the bid in a way that it can get some benefits. For example, if somebody bids very high to get resources easily, and then it pays less than what he is paying, it's kind of a cheating that we don't want in this situation. So a truthful auction says that you have to bid based on whatever you value the resource. So if you think that this resource worth $2 per hour for you, so you have to bid on that value. Any other values you are bidding, your utility function is not maximized. So optimal mechanism design or optimal auctions are those kinds of auctions that they are maximizing revenue for the cloud provider or for the seller. We have two types of mechanism. We have Bayesian optimal mechanism, and we have prior free mechanism. In Bayesian, we know the distribution of bids by clients, and based on that we do the optimal mechanism design. But in prior free, we assume that we don't know any distribution, and we try to maximize revenue for the cloud provider. Amazon Web Services offers spot instances. Spot instances are working in a marketplace that it is like auction mechanism. Clients of the cloud or users of the cloud service, they bid for VMs, and based on their bids, they receive VM machines, and then market price is changing, and if the price goes above your bid, you are losing your VMs, and if your bid is higher than the market price, you can keep using your resource. So inspired by Amazon Web Services spot instances, that they didn't reveal anything about the auction mechanism that they are using. We built a single price auction that is prior free, that we don't know any distribution about bids by customers, and it's envy free. It means that customers are not jealous of each other after they are receiving resources. For example, if you bid 2 and then another customer bids $3 per hour, and then you are getting the resource, and that person with $3 doesn't get the resource, it's not fair. So in these kinds of situation, we have sort of jealousy between customers. So our auction mechanism doesn't have jealousy, or it's envy free. And the other thing about our auction mechanism that we proposed is that it is truthful with high probability. Here I have an example of what is the problem. Let's assume that we have quantity of units of good, or for example, in this case, cloud resources, VMs that we need. For example, this user wants 2 VMs, or 1, 3, and another 5. These are the bids we are receiving for every request. For example, first user needs 2 resources with $8 per each resource. So the question is that what is the price that we should set here in this case to maximize the revenue for cloud provider? For example, if I set price single price in this case and I set price as $8, all these bits like $6, $5, $4, and $2 are out of bid, or they cannot get resources. So at the end, what we are selling is only 2 units of goods, and we are selling it at $8, so it becomes $16 of profit or revenue. But if I set it at $6, then it becomes 3 multiplied by 6, it's $18. So you can see by different prices we can set, we can get different types of revenue, and the optimal solution in this case I think is 5, that we can sell around 6 by 5, $30 of revenue we can make. So this is the optimal auction design in this case, but the problem of this method is that it's not truthful. For example, if this guy plays by, for example, the first user plays with the bid, it can increase or decrease the final price. So the suggestion is that we can, whenever we want to set a price for a specific user, we can remove his or her bid from the whole bid sets, and then we set the price based on the optimal single price that I explained here. This is good because it's MV free. It means that your bid doesn't affect the final price. So it's the best option is that you are revealing your real value. But the problem of this method is that it's not single price. If you remove, for example, user 3 here, user that wants 3 units of good here, the price might be different if you're removing the last bit. So considering all these backgrounds, we designed an algorithm that predicts optimal price by very accurate estimate in this case, and then we set the price on that estimate value we do, and this tries to maximize cloud providers revenue as much as the estimate is good. And the good thing about this estimation that we are doing, that I'm not going to the details of that, is that it's truthful by high probability. So the other thing that we did in this research is that we are calculating a reserve price for selling resources. For example, let me give you a airplane seat, aircraft seat as an example. If an airline company wants to sell seats of a flight to customers, and some seats are empty, you know, it's good to sell that that seat as at a very low price, because not selling it, it's like wasting that opportunity. But the question here is that how low we should sell that seat. Is that okay if I sell a flight from Australia, for example, to United States for $1? Does it make sense? I think in case of flight sets is very complex problem, and they have so many techniques to handle this situation. But the main thing here we should consider is the cost we are paying for that seat, if it is occupied or it's empty. For example, in case if somebody sits on that seat, at least it takes some, for example, foods or maybe some drinks, and this may cost something for the cloud, for the airline. So it's better than, at least we are not selling less than that. So based on this idea, we are calculating a reserve price for resources in cloud data centers, for in this case VMs. Because whenever you are running a VM, you are paying for the energy. So at least you have to sell it in a way that the price is higher than the electricity price you are spending for that running that machine. So based on this idea, we calculated a reserve price for a VM in our auction. So here we have some results. We compared our method with other methods, and you can see that our method is very close to the optimal in case of amount of profit makes for the cloud provider. The right figure shows that whenever your reserve price is not active, sometimes the profit is getting negative because you are selling it in a price that even doesn't cover your cost. As a follow-up for this research, we built a framework, open source software for pricing. This is that framework is called CPAS, and CPAS has a web services that can be used by cloud providers to get a price for their spot instances or their market they have based on the auction that we have here in the pricing module. So what we did, we added an extension module for OpenStack, and based on that extension module and communications happening between that module and our CPAS framework, we can set prices for customers. This is the screenshot of the page in the OpenStack dashboard. Here you can see, for example, you can bid for the resource, and based on the bids we are receiving and applying our auction method, we are setting price. Here you can this is another screenshot of our method in the OpenStack that shows that how price has changed based on the bids that people submitted into the system. To evaluate and validate our work, we conducted an experiment with group of cloud expert people. We asked them to sit and run their, they send their request to our system for bidding, and then our method is calculating price. And the idea here is that we want to see that if you are not truthful, maybe your utility function is not maximized. We created two groups of users. Group one, that they always submit truthful values into the system, truthful bids, and the second group that they are allowed to play with their bids, and they want to maximize their utility as much as they can. This is the final price, and as you can see, in some places the price goes to the maximum, and this is because some of the users from the second groups tries to add very high bid that kicks out other users from the auction, and they can acquire their required resources. But by doing this, they are their utility function is badly get affected because they are paying very high prices. Final result shows that those people who are truthful are getting the best utility values based on what we are expecting, and this is something showed in the results here. For example, lots of truthful users are getting good one. The only exception is here that the client tree or user tree that who has been allowed to cheat is getting a very high utility function. Utility value here is that this is happening because this user even though from the cheating group, he always makes a truthful bids into the system, and this is why he or she has got a very high utility value. The second study I want to talk is about renewable-aware geographical load balancing. We have a scenario that each data center is connected to two sources of power, grid and renewable energy, and then we want to distribute loads between these data centers in a way that we maximize renewable energy usage and we minimize brown or grid usage, power usage in this case. As you know, cloud data centers are power hungry. They are using a lot of electricity, and this may cause us high operational costs for cloud providers and also lots of carbon footprint in the environment. Based on the research by US National Resources Defense Council, in 2014, US data centers alone consumed around 70 billion kilowatts of hours of electricity. This is equal to 2 years of power consumption by all households in New York City, and this is equal to 0.4 million average households usage in that year. So this is going to be projected to make greenhouse emissions of 50 million tons of carbon into the environment. So because of all these statistics that I explained, cloud providers are aiming to reduce their energy consumption, and they want also to reduce their dependence on brown energy, and they want to reduce their carbon footprint. So renewable sources of energy is a way of doing that, and for example, in big companies like Google, Microsoft, and Amazon, they are building their own renewable energy sources to their own power generations based on the renewable energy to minimize their carbon footprint and their cost. So as an example, Amazon Web Services has built a wind farm in 2016 to exceed the 40% renewable energy production for their data centers that they have as a goal. But the problem of using renewable energy is that renewable energy is intermittent and unpredictable. And it's, for example, in case of solar or wind, we have, it's pretty hard to predict, for example, wind in near future and how much energy we can get out of wind, or solar energy has a daily pattern, and in the night we don't have any solar energy available. So because of that, as I mentioned, cloud providers, they are using mix source of energy, like they have grid as a backup, and they have renewable energy as a source for data center, for powering data center. And in case if renewable energy is not enough, they are using grid power, that in this case we call it brown energy. So even if we have two sources of energy, the question is that how we can maximize renewable energy usage, and how can utilization, and how can we minimize brown energy usage. Motivated by this question, we are suggesting geographical load balancing. That means that we can redirect load based on the availability of renewable energy in each data center. What is called in the literature as follow the renewable. We are trying to follow renewables in the different places that they are available. So the research question that we address in this study was that with limited or not in or with no in advance knowledge of future workload and dynamic and unpredictability of renewable energy, how we can maximize renewable energy utilization and how we can minimize cost and or brown energy usage. So here I give you an example of how complex this problem, geographical load balancing problem is. Let's assume that we have list of requests that are arriving, and load balancing algorithm wants to distribute them between two data centers here. Here each request has an arrival time and the quantity of unit capacity they need. For example, this request has one comes at time 1 and it needs 2 units of capacity or power consumptions here in this case, and this is the lifetime of the request. For example, in this figure you can see that request A stays for 4 time units in the data center and it uses 1 unit of capacity. Let's assume that white boxes shows renewable energy availability and the shaded boxes are showing brown energy usage. For example, in this case, for G, we are using brown energy. We want to distribute these requests between these data centers in a way that we can maximize usage of maximize utilization of renewable energy, and we are using less brown energy in this case. This problem is very complex because if you put your first request in the first data center, second request can go to the second or first data center, and all combinations like this tree should be calculated to find the optimal solution. So based on this idea, we built an optimal offline strategy that assumes that we know availability of renewable energy and future workload in advance, and then we want to make an optimal solution. And in our paper we showed that this problem is computationally intractable, and the time complexity of solving that is exponential. So even with knowing all information in advance, like future workload and availability of renewable energy, solving this problem is very complex. Because of that, we proposed an heuristic algorithm to solve this problem. And one of the applications that we thought is very good for this situation to do the load balancing is web applications, because it has very short size requests that it doesn't need it doesn't have duration in this case. That makes the problem a little bit simpler. So here is here is the figure shows the context of geographical load balancing we are doing. So we have multiple data centers. Each data center is connected in 2 sources of energy, renewable and grid, and we are getting web requests here at the load balancer. We want to distribute web requests between these data centers to maximize renewable energy usage. We proposed a framework for doing that. This framework has 2 layers of load balancing. At the top we have global load balancer that distributes loads between data centers, and we have a local load balancer in each data center that distributes load between web servers that we have on that data center. We have another component here which is called autoscaler. Autoscaler is responsible for adding extra resources if current number of web servers are not enough to handle loads we are receiving in this data center. We have a database server in the back end as well. If we are going deeper into the details of global load balancer, we can see that we have a decision module here. That decision module, based on the availability of renewable energy on each site and amount of power consumptions and the rate of requests we are receiving on the load balancer, make some decisions and sets weights for a open source load balancer that we have in this case, which is HA proxy, and HA proxy distributes load based on weights that we are setting by decision making module. The interesting part of this research is that we try to make everything realistic. So what we did, we used a testbed in France to run our experiment. The testbed is called Grid 5000. Grid 5000 is the research testbed in France. It has data centers around France, and these data centers are connected by high bandwidth networks. So we selected 4 sites here, Lyon, Nancy, Reims, and Rennes, because they are equipped with power metering tools that we can easily measure the amount of power consumption happening in each data center based on the metering tools that we have for each server. We built a prototype system. The prototype system is compatible with our overall architecture that we proposed previously. We have a local load balancer. Local load balancer has a HA proxy in this case that distributes loads between web servers, and we have a request generator here in this case that sends a request to the global load balancer, and the global load balancer, based on the weights that we are setting here, distributes loads between data centers. For the workload traces, in this case we used Wikipedia, and what we did, we downloaded the whole English Wikipedia database and we imported into that into our database. And Wikimedia Foundation released web requests for English Wikipedia in 2007, so we used 5% of this request for 19th and 20th of September to generate web requests. For pricing, we used price of electricity on the location of each data center based on the EDF website, Electricité de France, the utility company in France. And here you can see the price for these 2 days for different data centers. For renewable power generation, what we did, we collected meteorological data on the location of each data center, like solar radiation or wind speed at the location of each data center, and we built a model that based on that we can generate renewable energy generation in each site. Here we can see solar, wind for different sites, and here we have the combined version for those 2 days that we want to do the experiment. Here we have some results. This is our method, this is our heuristic, this is another method from the literature, and round robin that evenly distributes load between data centers. As you can see here, the green line shows availability of renewable energy, for example at Rennes, and black line shows the power consumption. As you can see, our method matches power consumption with renewable energy very well in these 2 data centers. Here we have some brown energy usage. The shaded area shows brown energy usage, and this is because we don't have enough renewable energy available in these 2 sites, and based on our algorithm we redirect loads to the first data center here, that is Lyon, that has the cheapest electricity price. The method from literature, we call it capping, is also doing equally good, but there are some minor differences that because they are using predictions and they have some linear optimization in this case. Round robin distributes load evenly between data centers, and it has lots of brown energy usage. As a summary, you can see that our method reduces brown energy consumption. Here we have 21.4 kilowatt hours of usage compared to the other 23 and 25.7 in case of round robin. And the total cost of execution of those 2 days requests in the data centers is 2.63 in our case, which is less than the other 2 methods. The last study I want to talk about is about building a test bed in our lab. We call it Clouds Pi. This test bed is for doing software-defined networking research in clouds. So because software-defined switches or OpenFlow switches are expensive to buy, so we used Raspberry Pi to build OpenFlow switches in this case, that I'm going to talk about lessons and experience that we had in this in setting this environment or testbed for our purpose. So before going to the details of testbed, I want to give you a brief introduction about software-defined networking. In traditional network, each switch, network switch, had two planes. One was the data plane or forwarding plane that was responsible for forwarding packets, and another plane was the control plane or the brain of the switch that makes the decision for forwardings and sets forwarding rules on the data plane. In software-defined networking, this part, the brain parts of switches, can be detached from the switch and can be run on commodity hardware. So, and from there it can control all switches. We have only forwarding plane, and this gives lots of flexibility in terms of managing networks and monitoring and running switches in commodity hardware. For example, in this case we have Cisco switches or Juniper switches that everything comes as a bundle, and if you want to do some changes on the hardware, on the software parts of the switch, is pretty hard and you cannot do it. But in this case you can easily change controller or that software-defined controller we have in the network. So we had some machines in our lab, for example 3 IBM servers, another 4 IBM servers of X3200, and 2 Dell machines, and we built up a cluster for doing research. So what we did, we made a switch out of a Raspberry Pi, modeled Raspberry Pi 3. Each Raspberry Pi has 4 USB ports, and then we use these adapters to add 4 Ethernet interfaces to the Raspberry Pi. We installed Open vSwitch on each Raspberry Pi, and then we made a factory-like topology for our cluster of machines that we have here. These are the physical hardware that we have. In terms of software, we installed CentOS 7 on all nodes, and we used the audio packet stack for OpenStack installation. OpenStack plays the cloud operating system in this case, and because we needed access to virtual machines we are running in the environment, so we had only one IP address here in this cluster, so we built up a VPN using OpenSwan and XL2TPD Linux packages for L2TP and IPsec virtual network, that virtual private network that users can connect to that network and uses their resources. As an SDN controller, we used Open Daylight. Is an open source SDN controller, and we used Open vSwitch on each Raspberry Pi as the software switch that makes that Raspberry Pi a 4-port switch for our purpose. Here is the system architecture. These are 8 machines working as a compute node, and we have the controller here. Controller hosts SDN controller, OpenStack controller, and plays the gateway to the internet. And we have 2 traditional switches here that are used for management network. But the data network here is that are used by VMs on the machines to communicate is going through the Raspberry Pi switches, as you can see. So SDN controller controls Raspberry Pi switches through that control network we have here. This is the final view of the CloudSpy platform. Here are the Raspberry Pi switches, and these are the servers that we have. To do some more some sort of case studies and validation of our platform, so we have got a topology like this at our platform. Here it's the topology showed by detected by ODL. These are Raspberry Pis and these are our hosts. So we selected two hosts with these IP addresses, and in the first use case we try to do some sort of dynamic flow scheduling between these two hosts. What we did, we generated some sort of synthetic network loads here, traffic between hosts, and then we find the shortest path between these two, and from the controller we dynamically change the route or path between these two machines. For example, if this route between these two hosts is crowded, we are using this path, or if this part of the path is getting crowded or packed, and we are using the other parts of network, because there are multiple paths in the factory like topology. So this shows that we can do dynamic flow scheduling using SDN controller, and we have the results here. Without dynamic flow scheduling, the amount of bandwidth we are getting between those two hosts is 35.24 megabits per second. But with dynamic dynamic flow scheduling, we could increase that bandwidth between those two, and also we decrease the transmission time between those two hosts. For the second experiments, what we did, we migrated a VM from this host to this host, and from there to this host. The idea is that if two VMs, for example, from host 1 here to this host are communicating with each other, when we are putting these two VMs closer to each other, for example, in this case in one pod, then the bandwidth between these two are increasing, because there is no contentions between the traffics of other VMs and these two VMs in this case. So what we did VM migration. As you can see in this figure, as time passes, we did 2 times of migration, and as you can see, the average bandwidth is increasing by doing the migration from around 70 megabytes per second to up around 90 megabytes. Because in this case, on the last stage here, we have these two VMs in the same pod, and they don't have they are only, the traffic is only going through one switch here. These are the two use cases that we used to show our platform is working and validates our testbed for future research. So in summary, what I want to say is that cloud computing is a critical building block for many ICT applications, and in future cloud computing becomes a critical part of most of IT applications. So in future, based on Gartner prediction, we can see more about things like blockchain and serverless PaaS, IoT platform, or container management, and etc. We talked about envy-free and truthful auction for maximizing profit for selling spare capacity of data center. We proposed geographical load balancing for maximization of renewable energy, and finally I shared our experiences for building an economical testbed for software-defined clouds. Thank you for listening, and this is the end of my talk.